Yeah.
Okay. All right, so what I want to do today is I want to continue applications of what we've done. So this is going to be a great way to review a lot of the stuff we've done all semester, to see how it comes into play, and then to see what comes next. A lot of what comes next is really rigorous limit theorems. And this is something we've touched on a little bit in this class, but not too much. I also want to talk a little bit about some of the research I've done with students over the past several years, most of it at Small. So a lot of the people who have done this have been Williams students who have just taken probability with me, haven't taken real analysis. So you already have enough background. If you're interested in stuff like this, I am happy to talk to you about opportunities like this for this upcoming summer. So the version I'm giving is a talk I gave at my alma mater, Yale. I was in Morse College last year. Okay, so introduction. So not much background is needed for these. I'm assuming everybody has seen the Fibonacci numbers. Okay? Fibonacci numbers have an enormous wealth of wonderful properties. So this is one of my favorites. My daughter and I, with a little help from Cameron, made this out of fuse beads a couple of years ago. How many of you have seen the Fibonacci Spiral? So the Fibonacci's are the only sequence of numbers that can fit together and spiral out. So 1 by 1, 1 by 1, 2 by 2, 3 by 3, 5 by 5, 8 by 8, 13 by 13, etc., etc. They all fit perfectly together and give you these chains of rectangles. This also gives you a beautiful theorem. The sum of the squares of the first n Fibonacci numbers is the nth times the n plus first, because we're counting the area two different ways. And each of these squares, well, the kth square is just fk squared. And this goes back to what we were doing in combinatorics. It all comes down to counting something two different ways. So what we're doing here is we're decomposing an area in terms of other areas. We're going to look at other decomposition laws using Fibonacci numbers. So a big part of what we're going to do is to try to find the right perspective to look at problems. There are many ways to attack things. You can slug through algebra, and I will show you how to slug through algebra. It's not enlightening. A huge part of the semester has been trying to find what way can I look at something so that it'll be illuminating, so I can see how things will simplify, so I can get a closed form expression that I can play with. Not surprisingly, generating functions are going to come into play with this. And then I'm going to end, if possible, with some open questions. It'll be a function of how fast the talk is going, because I want to leave time for the SCS forms. Okay, so quick probability review. We should know this all by now. You might have even seen this when we did the sabermetrics lecture. We have some random variable with density p of x. P of x is greater than or equal to 0. It integrates to 1. The probability we take on a value between a and b is just the area under the curve. This time I chose not to shade it. I had to be a little bit different. The mean is the integral of x p of x. The variance is how spread out things are about the mean. It's the integral of x minus mu squared p of x. And the Gaussian, which is extremely important, the central limit theorem, is 1 over square root of 2 pi sigma squared e to the negative x minus mu squared over 2 sigma squared. Okay, so what combinatorics are we going to need? Very basic stuff. I need that n factorial is the number of ways to order n people when order counts. N choose k, lots of different ways of writing it, is the number of ways to choose k people from n when order does not matter. And then Stirling's formula, n factorial is about n to the n e to the minus n squared of 2 pi n. One of my favorite proofs of this is using the central limit theorem applied to what random variable? Anybody remember? Poisson. So if you apply it to Poisson, where the parameter of the Poisson is n and goes to infinity, and look at the mean of that, you can get Stirling's formula with a decent error term. Hopefully you've all seen the Fibonacci numbers, if for no other reason that we've already looked at them this semester. They are defined by this beautiful recurrence relation. Fn plus 1 is Fn plus Fn minus 1. So the two previous terms completely determine the next one. And once I give you this, the entire sequence is defined. The only thing that we have a little bit of play with is the initial conditions. And depending on what you want to do, different initial conditions are better. So when we were doing, when we were doing the tiling like this, it was convenient to start the Fibonacci's as 1, 1. I'm not going to start the Fibonacci's as 1, 1. I'm going to start them as 1, 2. And we'll see in a moment why this is important. There's a beautiful theorem called Zeckendorf's theorem. Every positive integer can be written uniquely as a sum of non-adjacent Fibonacci numbers. Well, if I start with 1, 1, I lose uniqueness. If I start with a 0, I also lose uniqueness. So it makes sense to start 1, 2. It turns out that this is an equivalence. The Fibonacci numbers are the unique sequence such that every integer can be written uniquely as a sum of non-adjacent terms. The standard proof is with the greedy algorithm. So let's say I give you a number like 2012. You subtract the largest Fibonacci number you can from it, which in this case would be 1597, of course. You look at the remainder and you subtract the largest Fibonacci number you could from that, which here is 377. Imagine that 1597 and 377 were adjacent. Well, if they were adjacent Fibonacci numbers, what would be true about their sum? I'm sorry? It would be a Fibonacci number, which would be greater than 1597, so that would contradict the maximality of 1597. So this is the greedy algorithm. It's one of the most important algorithms in mathematics and computer science. It's a great way to constructively form things. And then we just keep iterating down. So the greedy algorithm will give you a decomposition exists. It does not prove the decomposition is unique. I'll leave that as a nice exercise. A really good homework problem would be to prove that you can't have two different decompositions. Now if you do the greedy algorithm, it will give you a decomposition. But it may not give you, but there may be another decomposition with non-adjacent summons. It turns out that there is only one decomposition with non-adjacent summons. It's the one that comes from the greedy algorithm. Okay. So, Lecoq-Coeur's theorem, and this is tough to say as a Bostonian, from 1952, is that the average number of summons in the Zeckendorf decomposition for integers between the nth and n plus first Fibonacci numbers is about n over phi squared plus 1, where phi is the golden mean. So whenever you see a theorem, you always want to look at what are the statements, what are the conditions, what am I studying? Why do you think I'm studying integers between the nth and n plus first Fibonacci numbers, and not all the integers up to, say, some number x? Why would this be a good thing to look at?
So you're going to subtract off fn and raise the first one of the things?
So when I do it like this, everyone is going to have an fn in it. All of my numbers are going to be approximately the same size. They're all going to have the same candidate list of summons. So they all have potentially n possible summons. If I looked at all the numbers up to some number x, some of them could be very small. Well, very few of them will be very small. Most of them, because the Fibonacci numbers grow exponentially, will be within, a little bit, maybe fn minus log n. They'll all be approximately having n possible summons. But this is a really good localization. They all have the same candidate set. What does this remind you of, this kind of standardization? Where have we seen something like this? In the central limit theorem. You're trying to compare, apples and apples. We're trying to standardize and have all of our numbers have roughly the same number of potential summons so that they're all comparable. The other thing that's nice is if you just stopped at some integer x, you might not stop at a Fibonacci number, and you might have to worry about edge effects. You can handle all of this stuff. It just makes it a little bit cleaner to stop here. So here's an old result, although my students and I came up with a new proof of this. As n goes to infinity, the distribution of the number of summons converges to being a normal. And it turns out it's actually very easy to do some computer simulations and deal with extremely large numbers. So, if you're around the 2010th Fibonacci number, the number is going to be of size 10 to the 420. The way you can work with such huge numbers is you just store it as an array. How many digits would a number of size 10 to the 420 have? 420, right? Maybe 421, I don't know. But it has on the order of 420 digits. If you store your number as a list, all we're doing is we're doing addition, subtraction. You can do these on lists extremely fast. So we can deal with extremely large numbers and get wonderful data far off. You want to talk about convergence, great. I'm pretty far down in terms of the size of my number. Although the real guiding factor is not the 10 to the 420, but the 2010. You could probably also figure out when I first started looking at problems like this based on the plot. Here are some more interesting questions which we then studied in later years. We're looking at gaps now between summons. So how long do you have to wait once you have a gap till you have the next one? And there's lots of ways of doing it. So what we can do first is you give me some number m. Oh, I lost the laser. Wow. Okay, so interesting. All right, so you have some number m, and we can decompose it as a sum of Fibonacci numbers. They'll be non-adjacent. We won't have two next to each other. And because I'm in this interval, I have to have fn as one of my summons. So that's why, I go all the way up to km, my number of summons, I'm going to go up to n. What I can do is for each m, what I'm going to do is we looked at the delta function when we did random matrix theory. It's the same idea. We're going to apply it here. I have km minus 1 gaps between summons. There's no gap to the first one, and then between every 2 subsequent ones I have a gap. And I'm going to put a mass of 1 over km minus 1 there. And so this is very similar to what we did in random matrix theory. And it turns out that the gap measures converge almost surely, this is just the technical statements, to geometric decay. Now, one of the big issues is how do you present information in such a way that people will be able to see it? Well, if I plot it like this, it kind of looks like that could be geometric decay. If it's geometric decay, I should have a common ratio in terms of the relative sizes of these. And that's what I've plotted over here. And it's 1 over phi to the k, where phi is the golden mean, so I should have a constant line at the golden mean. And we see that when we look at plots between adjacent ones. Now what's particularly interesting is it almost looks like it's forking out over here at the end, with some maybe kind of alternation. I'm not quite sure why. Is there some explanation for what's going on here? Do you have a phenomenon like this? Do these oscillations start to get larger as you go further down? Lots of stuff that can be looked at. There are several ways you can study questions like this. One possibility is we can fix a specific value of m, and for that specific value of m, we can then look at the individual gap measure. And then the hope is very similar to random matrix theory. Almost all gap measures will be very close to the system average. And this is the system average. It's much easier to look at the system average. What that means is take every m in the interval, and for each m you have a bunch of gaps. Throw all those gaps into a giant cauldron, and then put all the gaps of length 2 in one place, all the gaps of length 3 in one place, all the gaps of length 4 in one place, and ask, as you go over all m, what fraction of the time do you have a gap of length 2, of length 3, of length 4? Why aren't I concerned about gaps of length 1?
Non-adjacent.
Yeah, they're non-adjacent. You can't have a gap of length 1. Another thing you can do is longest gap. So if I give you an m, what's the probability distribution of how long you have to wait before you have another summoned? Well, okay, that's what we just did. But a related question is, what's the longest you expect to wait? Not surprisingly, the more summons you have, the more likely it is that you have a longer wait somewhere in. So this goes back to a very similar, simpler problem. Say you have a fair coin and you flip it a lot of times. What's the longest run of heads you could have, or the longest run of tails you could have? We analyzed this before. Where did we analyze this?
The roulette problem.
The roulette problem. Trying to calculate what's the probability you have a gap of length 5. So we didn't calculate the distribution of the longest gap. We just calculated the probability you have a gap of length 5. But you can expand those techniques and try to come up with a distribution for the longest gap. One of the reasons I really like this problem is that we have a double exponential occurring in a very nice way. Where have we seen a double exponential before? So one other time this semester. So this was the moment generating function of the Poisson. The moment generating function of the Poisson actually had a double exponential occurring in a natural way. Let's look at what's going on here. So as n goes to infinity, the probability that it has a longest gap less than or equal to fn converges to the following. So this is the cumulative distribution function. This is the probability my longest gap is at most fn. As fn gets larger and larger and larger, the probability should be approaching what? I'm sorry?
Infinity?
Oh, we can't have probabilities approaching infinity.
Oh, right.
So correct it to not infinity,
One.
to 1. So as fn gets very, very large, the probability should be approaching 1. Well, let's see. If fn is very, very large, the largest fn could be is on the order of n. Log of n minus n, even divided by a constant, this is going to be a huge number over here. E to a huge number is a huge number. But it's a huge number with a negative sign, right? What's e to a very large negative number? 0. And then e to the negative 0 is 1. So as fn goes off to n, we get a probability very close to 1. If fn is a little bit smaller than phi of n log n, well, log is log phi of n, log phi times log of n. So let's say that this is going a little bit slower than my predicted mean of log n. If this is just a little bit less, then my exponent of e is going to be a positive number. A positive number tending to infinity. What's a positive number tending to infinity? What does that look like? It goes up to infinity. Now we have e to the negative positive infinity, which goes to 0. What this tells you is if you're just a little bit below the mean, the probability is essentially 0. If you're just a little bit above the mean, the probability is essentially 1. It is a very, very sharp transition. This is one of the few processes I know that has such a sharp transition. When we do the central limit thing, we say, we have n objects, we expect maybe n over 2 if we're tossing coins, we expect fluctuations in the number of heads to be on the order of square root of n. In something like this, the mean is essentially log phi times log of n. And let's say you're log n smaller. That's negligible relative to the mean. But that's enough to make the probability essentially 0. Similarly, if you're log n larger, that's enough to make the probability essentially 1. The variance of this process is actually bounded independent of n. Same thing with the coin tosses. It's extremely sharp when you do this. It's remarkable how sharp this is. Right. So I want to now review one of my favorite problems from the whole semester, the cookie problem. So this is the key idea. This is the contribution I added to the literature, is people were not using Cookie Monster to try to prove results in the subject. They were using continued fractions, which is a horrible, horrible mistake to be making. You should be using Cookie Monster. On an interesting personal note, I was first doing this when my son was back in the children's center, and he had been bitten by his best friend again that day. And so back then they wouldn't tell you, who bit your kid, but they would give you a little note at the end of the day saying, and so the original calculations were actually done on the back of a note saying, Cam was bit by Anonymous. Alright, so the number of ways of dividing C identical cookies among P distinct people is C plus P minus 1 choose P minus 1. This is such a great concept I want to go through the proof again. So we have C plus P minus 1 cookies in a line, Cookie Monster comes, he eats P minus 1 cookies. How many ways are there to do it? Well, that's the whole definition of n equals k. And it divides the cookies into P sets. So if you want, imagine we have 8 cookies and 5 people. Cookie Monster comes. Cookie Monster eats 4 cookies. Then everything up to the first cookie goes to person 1, so they get 2 cookies, 0, 2, 3, and 1. There's a one-to-one correspondence between the number of ways to choose P minus 1 cookies from C plus P minus 1 and the number of ways of dividing C identical cookies among P distinct people. Most mathematicians don't like to talk about Cookie Monster, so they want to rephrase this into a more boring language. So this is called a Diophantine equation. So a Diophantine equation is when you're trying to solve a nice relation involving variables that take on integer values. So here, we want to count the number of solutions to x1 plus xp equals c, where the xi's are greater than or equal to 0. Well, that's the cookie problem. And just x1 is how many cookies the first person gets, and so on and so on and so on. Oops. So let's see how this is now related to the cookie problem, to the Zeckendorf problem, to decompositions. So I'm going to let p and k be the number of integers in my interval whose Zeckendorf decomposition has exactly k summits. So this is something that had not been done before. This is very similar to our idea of partitioning our set into events. When was the first time this semester when we partitioned into distinct events?
Day one.
I'm sorry? Day one. What did we do on day one?
I wasn't in class then.
You are correct that we did it on day one. What was it that we did on day one?
We flipped a coin.
No.
Birthday problem?
I'm sorry?
Birthday problem?
It was not the birthday problem.
Basketball problem.
It was the basketball problem. We looked at how many ways were there for Bird to beat Magic. And he could beat Magic on his first shot, on his second shot, on his third shot. And if Bird beats Magic on his first shot, he's not also going to beat him on the third shot. So there was just one way of winning, either on the first shot or the second shot. You can't be winning simultaneously on the first and the third shot. And we calculated the probability of each of those events, and we added them together. It turns out it is much easier to break the analysis like this. And if we do it like this, what we're able to see now is P and K, well the N not surprisingly is because we're looking at the interval Fn to Fn plus 1, and the K means we have exactly K summons. So let's see what that means. If we have exactly K summons, well the last one has to be Fn, we have K minus 1 before, we have the indices. The smallest the index can be is 1, the largest it can be is N, which is the last one, and because they're not adjacent, ij minus 1 is greater than or equal to 2. Whenever you're seeing a talk with algebra, don't try to follow all the algebra, just try to follow the general flavor of what's going on. Well, this is the same as the cookie problem. Let's let d1 be I1 minus 1, dj ij minus 1 minus 2. For each gap, I'm subtracting what it's forced to be. So the d's are the excess over what they must be. And the reason is, this is like the cookie problem, where I now require the first person gets at least 1 cookie, the second person gets at least 2 cookies, and so on and so on and so on. So when we just put all this in, it's now the same as the sum of the d's is n minus 2k plus 1. That's the cookie problem. We have a closed form expression for how many numbers in this interval have exactly k summons. It's just n minus k choose k minus 1. And if we want to prove it's a Gaussian, what do we have to do? We just have to show that this converges to be normally distributed. Now, unfortunately, there are more general problems you can do than just using the Fibonacci numbers. You can study other recurrence relations, other processes. And in general, we are not going to be lucky enough to have a closed form expression like this. So the proof I'm about to give you is a bad proof in that it does not generalize. But it's a very good direct proof, and it allows me to review Stirling's formula. So my students proved this back in 2010. And the proof basically is just use Stirling's formula and show that n minus, was it n minus 1? No, n minus k over k minus 1 converges to the density of a Gaussian. So all we have to do is go through the algebra. I had to decrease the font size to get things down to a reasonable number of slides. So here we go. This is, I've just shifted things. It was a little bit technically convenient to shift our interval over by 1 so I could get rid of some of the n minus 1s. So this is the number of integers in that interval that have exactly either k or k plus 1 summons, and I'm dividing by the number of terms in my interval. And now I just go through and I start doing the algebra, or my students do the algebra, and they do more algebra. We take logarithms because they're working with me, they know they have to take logarithms at some point. Do some more algebra, continue doing some more algebra, expanding things around, do some more algebra, a little bit more algebra, and finally at the end of the day, they get the density. And amazingly, they were still talking to me at the end of the day. So this is a great example of a follow your nose proof. You will get the right answer. Almost surely you will not get it on your first attempt or even your second or your third attempt. Why do you think it took them so long?
Lots of algebra.
Oh god, yeah. I mean, the number of algebraic mistakes and all of this stuff was horrible, and forgetting factors and whatnot. Now at the end of the day, we know it has to integrate to 1. It's a probability measure, so we could use that to at least sometimes figure out where we missed some factors. But this was an algebraic nightmare getting this to work. But they got it within a week, and I knew they would. The question was generalizing. So what I want to talk about now is one class of generalizations, what I'll call linear recursive sequences with arbitrary non-negative coefficients. One of the big things we want to do is we want to weaken some of these constraints as much as possible. I don't want to go into all the details now, I just want to give you a flavor of the subject. So we have some recurrence relation like this. So very similar to what we did with roulette. These are great ways of modeling things in the world. I'm going to have a fixed depth. So L is fixed. It's going to be at least 1. My coefficients are going to be non-negative integers, and I need to assume that the first coefficient is greater than or equal to 0. In fact, I need to assume that the first coefficient is strictly greater than 0. There's some work I'm doing with some colleagues now where we are handling what goes on when C1 is allowed to be 0. You can actually get different behavior for some questions. It's very similar to what we saw in random matrix theory, where the density of states could change, but the gaps between the states was universal. I think it's the same thing here. I think you're going to get differences in some of the counts. You actually lose uniqueness in some cases, but I think the Gaussianity will still hold. So we have the following 3 theorems hold in this great generality. There's a Zeckendorf theorem that there's some kind of legal decomposition. I don't want to go into exactly what the correct generalization of the rule is. If you think about what we were doing with the Fibonacci numbers, what does no adjacent mean? It means, well, the Fibonacci's are defined by Fn plus 1 is Fn plus Fn minus 1. If we ever have 2 things that are adjacent, we can combine them. So as a quick rough rule, think that the legal decomposition means I can't use my recurrence relation to remove anything and simplify. That's not entirely accurate, but it's a pretty good approximation. There's also, sorry, wrong direction. There's also a theorem in terms of the mean and the variance, and there's also a central limit theorem. There's also results about gaps and whatnot. The theorem becomes a little bit more complicated. The coefficient before was really nice. It was, n over phi squared plus 1. Now over here, the constant c in front of n, instead of being 1 over phi squared plus 1, is this god-awful mess where the s's are defined by partial sums of the c's, y's are roots of various polynomials and several variables. It's amazing the students are still speaking to me. It gets really bad. In the past few months, I have just found a way to bypass a lot of these technical obstructions, and one of the projects I want to do this summer is actually mine and see how far we can do with that. But we can write down closed form expressions for what these are. What made this so difficult is if I give you the recurrence relation and you go to a computer and you calculate things, everything is fine and you can check all the conditions you want. But we had to prove a lot of results in general about polynomials. The big idea that I had a couple of months ago was we can prove very easily that something holds with the form Cn plus d, but we need c to be greater than 0. And the way you prove c is greater than 0 is you do a lot of nightmarish calculations involving roots of general polynomials. And prove that if the c's have these properties, then your resultant c will be non-zero. And it's held. The new idea I just had is, well, why don't we just assume c is 0 and get a contradiction? Turns out that's much easier. And if c turns out to be 0, you don't actually have enough terms. And the number of numbers up to n is less than n. And since there are n integers up to n, contradiction. So you can actually bypass a lot of the technicalities. We still have a central limit theorem. What I want to do now is I want to give you a rough idea of why the central limit theorem holds. Let's consider a very special case. And again, this is one of the big themes of the course. If you have something new, if you have something complicated, especially those of you who are going to be doing job interviews, look at a special case and try to build intuition. We're talking about decomposing numbers as sums of non-adjacent Fibonacci's. I am pretty sure none of you, or almost all of you, or almost none of you have done, I'm phrasing this probably poorly. I'm pretty sure most of you have never tried to write an integer as a sum of non-adjacent Fibonacci numbers. Maybe 2 or 3 of you have tried to do this. Most of you have not, for good reason. Most of you have probably written numbers in terms of sums of ones, tens, hundreds, thousands. Right? We've been doing this for, since kindergarten, first grade? My kids are now doing this through Common Core, and they hate having to draw all these number pictures with all the stuff like this. So you guys lucked out. You got to do this before that stuff. Let's go back to what you've seen. So let's let hn plus 1 be 10 times hn. h1 is 1. hn, well, this is a very simple recurrence relation to solve. If each term is 10 times the previous, it's going to be 1, 10, 100, 1,000. My legal decompositions are just decimal expansions. So now you give me some number and I just write it in decimal. Now my coefficients in my expansion is going to be how many times I have hi. So all of my numbers are either 0 through 9, or if I'm the leading digit, 1 to 9. Alright, so now I choose an n in my interval, and so the first term is going to be my highest power of 10. So the first one is going to be from 1 to 9, everything else is going to be from 0 to 9. Let's look at as we vary over all the possible integers in the interval. This is beautifully set up for the central limit theorem. We can choose the number of ones, the number of tens, the number of hundreds, the number of thousands independently. They're just uniform random variables on the discrete set 0 through 9. So we choose the number uniformly from 0 to 9 for the ones digit, uniformly 0 to 9 for the tens, uniformly 0 to 9 for the hundreds. And we add them all up, and then we have to be a little bit careful. The last one is only 1 to 9, not 0 to 9. So the sum is not a sum of independent, identically distributed random variables. What I did is I said, screw that, let's just forget about A1. In the limit, it's not going to matter. If you wanted to, you could put in A1, not a big deal. What do we know about sums of independent random variables that are identically distributed and nice? Gaussian goes to a normal, central limit theorem. This is one of the nice applications of what we did. So this will converge to a Gaussian. We can calculate the mean very easily. It's 4.5n. with some small error term, and we can calculate the variance. So in the special case of decimal expansions, we now see why Gaussianity is not something unreasonable. It's a little bit harder to then say, well, then this will also apply to the more general case we're looking at. It turns out that's true. Okay, any questions about the sketch of the proof here? So this is a really nice application of the central limit theorem, and you can see the sums of the independent random variables. All right, here's a couple of other interesting variations you can do. So another nice one is, rather than just using the Fibonacci numbers, what if you allow yourself to use signed Fibonacci numbers? So you can use both positive and negative Fibonacci numbers. So if you want to do 1900, it would be f17 minus f14 minus f10 plus f6 plus f2. And it turns out you can write every number uniquely as the sum of signed Fibonacci's, such that two terms of the same sign, different index by at least 4, and opposite sign, different index by at least 3. Let's let k be the number of positive terms and L the number of negative terms. They converge to basically phi over 2. I'm sorry, the difference between them converges to phi over 2. They both converge to roughly n over 10 in terms of the number of summons. This is slightly fewer summons than in the Fibonacci case. Are you surprised that we have fewer total summons than we do in the Fibonacci's? Why is it not surprising? It's not just the case where we could just say, well, let's just only use positive summons, because now we have to be differing in index by at least 4 if we always use positive summons. Why is it not surprising that we have fewer summons? Yes?
The most we could have is fewer than the most we could have in the other case.
Why?
Because of the requirements on the signs, on the summons being differing by at least
Right.
3.
So if the legal decomposition exists, it will have fewer summons. Because now things are different by either 3 or 4 rather than different by 2. But maybe in the Fibonacci case it says we always have to have a gap of length at least 2, but maybe in the Fibonacci case we typically have gaps of length 5, 6, or 7. So unfortunately that's not quite enough.
But in the Fibonacci case, since it's unique, since every sum is unique, doesn't every sum that satisfies the requirements?
So good. So and that's one of the counting arguments. So every legal choice of index corresponds to a number. But there's another intuition, so you've got a good reason, but there's another reason as to why it's not so surprising.
Are there like more kind of numbers at our hand since we can construct other numbers from the difference? Like,
so you have a little bit more freedom with the differences. What you can do specifically is you can overshoot. So remember, the Fibonacci's are exponentially growing. We take the largest Fibonacci number we can. What if we miss by just, our largest Fibonacci number is much, much less than our number, which happens to be 1 before the next Fibonacci number. Oh crap, if it's 1 before the next Fibonacci number, I'm going to have to use a lot of summons to get up to it. What I would much rather do is, screw this, let me overshoot by 1, and then subtract that off. So sometimes it's better to do something like that. And so one of the reasons I want to talk about this is just methods of attacking things. It's sometimes better to overshoot and then fall backwards. What I like is, we haven't done too much about bivariate Gaussians, but for those of you who've done statistics, it's actually K and L converge to a bivariate Gaussian with correlation coefficient related to the golden mean. So it's wonderful how many places the golden mean shows up. So, have I gone through these slides with Benet's formula? Have we done that in this class? So, then very quickly, we have the recurrence relation. I know I did this on the board. We have a generating function, we put in the fn's. We then use fn plus 1 as fn plus fn minus 1. We substitute, we shift indices around. You also do this in differential equations when you're playing some of those games. We now want everything to be xn, not xn plus 1 and xn plus 2, so we pull out some x's. We then add the missing terms we have so that everything is a full sum from 1 to infinity. We write this as g of x. We then solve g of x as x over 1 minus x squared. Now that we have a generating function in closed form, we use partial fractions, we decompose, we expand each one of these using the geometric series, our old friend again, and here's Benet's formula. So we see that if we have a generating function and we have a closed form expression for the generating function, we can do a lot. That's the whole point of this, is we want to get a closed form expression for the generating function. Good, another friend to talk about, differentiating identities. So let's go back and quickly review differentiating identities. So, so imagine, the probability x equals 1 is a half, probability x equals 2 is a fourth, x equals 3 is 1/8. So this is a nice geometric random variable. What's the mean of x? Well, we saw we could calculate the mean, if we have a generating function like this, 1/2 x plus 1/4 x squared plus 1/8 x cubed, etc., etc., etc. We have a nice expression in terms of x. We differentiate, we get 1 times 1/2, 2 times 1/4, 3 times 1/8. And now if we just set x equals to 1, we get the mean. So this is phrased slightly differently than what we did before. Before I wouldn't have had the coefficients 1/2, 1/4, 1/8. I would have just set x equal to 1/2. Here I'm setting x equal to 1. It's just a matter of which gives me cleaner algebra for what I want to do. But this is one of the powers of generating functions. If you have a nice closed form expression, I just have to differentiate this and set x equal to 1, and I will get the mean. If I take the second derivative and do some tricks to it, I should be able to get the variance, and so on and so on. And so we use the method of moments, we calculate the moments of these, and so they go to the moments of the Gaussian. And the moments of the Gaussian are just 2n minus 1 double factorial. What I want to do now is show you where recurrence relations can go. And I think what I'm going to do on Fridays, I'm going to end with the M&M game, which is going to give us recurrence relations in 2 indices, which is a little bit more interesting. So Pnk, as we said before, is the number of integers in our interval where we have exactly k summons. We want to get a nice expression for this. We can do that for the Fibonacci's, we can't do that in general. So what we're going to have to do in general is have a generating function. So let's count how many n in the interval fn plus 1, fn plus 2 have exactly k summons. Well, that's by definition Pn plus 1, k plus 1. I have to have fn plus 1. I can't have fn, but I could have fn minus 1. If I have fn minus 1, how many remaining summons do I have? Including that, I have to have k summons. I have to get to k plus 1 summons total. If I have fn minus 1 as a summand, then fn minus 1 plus all the remaining summons, that must add up to k summons. If I don't have fn minus 1, maybe I have fn minus 2. And then I have to have k summons from that point onward. So I get this beautiful relationship. Pn plus 1, k plus 1 is Pn minus 1k plus Pn minus 2k plus dot 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 dot. It's a recurrence relation. It's not, unfortunately, a constant depth recurrence relation. It goes all the way down to the beginning. We don't know how to solve that. But we can again use one of our key tricks. We talked about calculating the probability of exactly 5 as your longest gap. How do we calculate the probability of exactly 5? What's the trick to get exactly 5? So how do we do exactly 5?
Inclusion, exclusion?
You could do inclusion exclusion.
You do at least. And
At least 5, and then subtract off.
one.
At least.
Four.
At most
So
four.
You want a gap of at least. You want a gap of exactly length 5. So you take a gap. It has a gap of length at least 5, and you subtract off. It has a gap of length at least 6, and the difference will be a gap of length exactly 5.
Yeah.
Or probably in this case, we want a gap. We want the longest gap to be 5. Well, at least 5. Something along those lines. And so when we do the subtraction like that, we can get very nice expressions. So now we did integers in fn plus 1, fn plus 2. Now we go back to the original interval and we do Pn k plus 1, and we get this nice relation. And notice, you can have massive cancellation. So you get Pn plus 1, k plus 1, bring this over to the other side, is Pn k plus 1 plus Pn minus 1k. So you now get a nice relation of depth 2, but it has 2 indices. You have seen something similar to this in the semester. This is a little bit harder to remember where we've seen this.
binomial.
Binomial theorem, excellent, Pascal's triangle. There are ways to solve things like this. And so we can form a generating function using these numbers, and it turns out this generating function is now going to be of 2 variables, one for the k, one for the n. We get a beautiful expression involving x and y. It's not a bad function. And then the coefficient of y to the n is going to be what we want. You can do differentiating identities, you can calculate everything you want, you get sequences of moments. If you do the Fibonacci case, the generating function is coming from a very simple recurrence relation, and it's a nice situation. Here's our generating function. If you look at the more general case, the recurrence relation is much more involved, and the generating function is a lot more involved. And again, the students are still speaking to me. You can analyze these things and get closed form expressions and get Gaussian behavior. The partial fraction decomposition becomes much, much worse. It can all be done. Alright, so I want to take another 2 or 3 minutes and then just quickly do some stuff about gaps in the bulk, and then I'll give the rest of the time to doing the SES. So let's look at the distribution between gaps. So the gaps are going to be the differences between adjacent terms. So it'll be in minus 1 all the way down to I2 minus I1. So if I have this as my decomposition, I would have a gap of length 10 and a gap of length 7. Let's let P and K be the probability that I have a gap of length K. And I'm going to allow myself to vary over all numbers. And I want to know, does the limit exist? You can ask similar questions about other types of decompositions. Here's results. Instead of doing things for base 10, you can do things base B. What I like is you can quickly check and see, is this reasonable? If you do things in base 1, the only numbers you have in base 1 are 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. There shouldn't be any gaps. And you'll see something like that happening. Okay. We can get the formula in general for a positive linear recurrence, and you end up getting geometric decay once the gaps are sufficiently large. And again, we have some technical conditions on the C's that I would love to remove. So here's a quick sketch of the proof of the Fibonacci's. The total number of gaps is the number of numbers in my interval times the average number of sums. I'm going to introduce xij to be the number of integers whose decomposition has fi and fj but nothing in between. So the bane of probability in combinatorics is double counting, and I want to make sure we never double count something. So an integer m could be counted multiple times if it has multiple gaps of length 5. What I want to do is, for each index I, I'm going to look, do I have a gap of length 5 starting at I? If so, I count it. And then we just count how many of these we have for given k, and that'll give me a gap of length k, and I divide by the number. And so now we want to know is how many decompositions contain a gap from fi to fi plus k? Well, very quickly, it turns out it's the product of 2 Fibonacci numbers. And the reason is, let's say I have fi, and I have fi plus k, and I have nothing in between. Well, then I need to fill in all the stuff up to fi. And this is exactly what was mentioned earlier. Anything that's legal is now allowed. So I now look at how many legal ways can I fill in stuff over here. And that turns out to be fi minus 1. You now look at how many legal ways, well, if I have fi plus k, I can't have fi plus k plus 1, but fi plus k plus 2 is now legal, and you can see how many you would have in something like that. You multiply, you now have product of 2 Fibonacci's. You can use Benet's formula, you can use generating functions, and you turn out to get a beautiful geometric decay. So I hope this gives you, a sense of the types of problems you can look at. I'm not going to go into longest gaps. If you want, that's there. You can take a look at that. This gives you a sense of the tools we've been using. It's a great way of reviewing a lot of the stuff we've seen. All right, so I have a semi-responsible person. Yes? So when you're done, please hand in your SES forms over here. Turn this off.